In this chapter, we will take a look at sensitivity analysis. We will examine how changes in the parameters will influence the mathematical model. Such a sensitivity analysis is normally performed before data collection. So what you will do is you will collect a very small sample, and with this sample you will look at the influence that parameters have on the model to determine the important variables. Once you have determined the important variables, it makes sense to put more effort in accurately measuring or collecting these variables. But before we go to the sensitivity analysis, we first need to introduce the concept of Monte Carlo simulations. A Monte Carlo simulation is a computational algorithm, so it happens completely in silico. This algorithm is based on a large number of simulations, thousands up to 10,000 of simulations, and on repeated random sampling from distributions. This, of course, means that you have to have an idea about the distribution of your variables. To know the distribution of your variables, you can either have experience or you can look up a similar experiment and see what distribution is used there. Or you could perform a preliminary study, so taking a very small sample and see how the data are distributed in that sample. Monte Carlo simulation is a very popular technique, and in our case we will use it for stochastical modeling, for global sensitivity analysis, and for uncertainty analysis. The principle of a Monte Carlo simulation is very easy and always follows the four same steps. First, you take your model and you determine which of the parameters and the variables in this model are stochastic. So which of them are variable and on what interval are these variables or these parameters living. Then you will generate a sample of a chosen sample size. So you will create deterministic sets of the model constituents using their probability density functions. Next, using this created sample, you will do a deterministic simulation. So you will apply the model to this sample. This is called a shot. And then finally, you do a statistical analysis of the simulated results. To make it more clear, let's visualize this. First off, you have your model. This model has a certain number of inputs, and these inputs, at least the stochastical inputs, they have certain distributions. Based on your theoretical model, you will then do a Monte Carlo simulation. This simulation will create a sample, a shot, which you then input into your deterministic model. By plugging this shot into the model, you get a result, a discrete result. And then finally, you will analyze this result using statistics to get an idea about the output of the model and, for example, its distribution. So let's say we have a model with two variables, x1 and x2. We know that these variables are stochastic, so we need to know their distributions. Then we will perform 10,000 simulations. This gives us 10,000 samples of x1 and x2. We plug these into our model to get 10,000 values of the output y. We analyze these outputs through a histogram, for example, or a box plot, and this gives us an idea about the distribution of the output y. We can split this scheme in two parts. The left part is completely probabilistic, so here is uncertainty. The right part is deterministic, there is no uncertainty. So the right part, everything happens on my shot. This gives me a deterministic result. But once we move back to the statistical analysis, we again have probabilistic uncertainty in everything that we do. So for example, if x1 would follow a Gaussian curve, x2 is uniformly distributed on a certain interval, we plug it in our model, we do the simulations, then we could, for example, see that the output y for this given model follows a chi-squared distribution. Monte Carlo simulation comes with some practical problems. First of all, you need to determine the probability density functions for all the stochastical components. Sometimes this is easy, other times this might be a lot harder. How can you do it? You could do repeated measures, so you could do a small sample and see what happens on this sample. You could know a confidence interval of the estimated parameter. You could determine it through literature study or through expert knowledge. The second part is that it requires a large number of simulations, so it is a computationally very intensive method. Of course, the more complex the model will be, and the more parameters you have, the more heavy it will be on your machine. How to perform the sampling? The most trivial way is just use random sampling. So for example, we have two variables, a variable u, which is uniformly distributed on the interval 0, 10, and a variable v, which follows a triangular distribution on 0, 10. Since you know the distribution, you know the cumulative distribution function for each of the variables. To then create a random sample of two-dimensional vectors uv, what you do is you pick a random number between 0 and 1, so a random probability for the variable u, and then you transform it back to find the value of u which corresponds. So for example, in the first step, let's say that the outcome is 0.63. Then you use the cumulative distribution function to find that this corresponds to a value of 6.28 for my random variable u. You do the same for v. For example, the random number there is 0.49. You transform it back to v itself, and then you see that v has a value of 6.26, which gives me my first observation, my first simulated observation of 6.28 and 6.26. And then you repeat this process until you have a sample of your desired sample size. This will create a completely random sample, but there is also a drawback. As you can see on the slide, this random sample is mostly concentrated around the values of the random variables with the highest probability. And so a lot of the time, very often, if you do random sampling, there are big parts of the sample space which are not sampled, so which remain empty. So here you see, for example, that the entire lower corner has not a single observation. To remedy this, we could do Latin hypercube sampling. Latin hypercube sampling will generate a near random sample of a multidimensional distribution, but not a fully random sample. However, this technique is often used in computational experiments and for Monte Carlo. In the context of statistical sampling, we say that a square grid containing sample positions is a Latin square if and only if there is only one sample in each row and in each column. So this example is a Latin square because every column and every row has exactly one observation. The other example is not a Latin square because, as you can see, the second row has two observations in it. A Latin square hypercube is then just a generalization of a Latin square to more than two dimensions. How will we now perform Latin hypercube sampling? Well, we divide the range of the variable into m equally probable intervals. So equally probable means that they have the same interval length on the y-axis of my cumulative distribution function. Then in each of those intervals we will take a random number and we bring it back to find the corresponding value of the variable. This gives us, for example, 4 values of my first variable, 4 values of my second variable, and then we randomly combine the values of the first one with the values of the second variable. Of course, each of the sampled variable values is only used once, otherwise you will not get a Latin hypercube. By performing such a Latin hypercube sampling, you are more certain that the data are spread over the entire sample space, but they are no longer truly random. However, if the sample is large enough, it will be a very good approximation of a random sample. If we then perform this on our example, so U is still the uniform distribution on 0, 10, V is still a triangular distribution on 0, 10, we divide each of the ranges of the probability into 5 parts, and in each of those subintervals we take one random value and we find the corresponding value of the variable. So for example, for the random variable u, we have in the first interval a random probability of 0.14, which corresponds to a value of u of 1.39. The second interval we had a random value of 0.27, corresponding to a value of u of 2.69, and so on. So we do this for u, and we do this also for v. As you can see in the right figure, Once that the distribution is not a uniform distribution, the intervals on the x-axis will not be of equal length. These intervals are chosen in such a way that the probability for each interval is the same, but because the mass is distributed differently, the interval length on the x-axis will not be the same. So that's why we have to divide the y-axis in equal intervals and not the x-axis. So this sampling gave us 5 values for the random variable u, 5 values for the random variable v, and then we randomly combine them. In this example, we see that the first value of u, 1.39, is combined with the fourth value of v, 7.57. Further, we see that the second value of u is combined with the second value of v. The third value of u is combined with the first value of v, the fourth value of u with the fifth value of v, and then finally the fifth value of u is combined with the third value of v. And then you see that the final random sample is more evenly spread over the entire space.